Welcome to breadboarding. In the previous video we covered the introduction to breadboards and we managed to get a simple breadboard circuit with LED and a USB power supply. So this was power coming from a standard USB charger. And we tried a number of different resistor values to see what the current we would get through the second LED here. And what we found really was that even with a 1K resistor, then the brightness of the LED was sufficient. And we didn't really need the 330 ohm one that we had on this other one here. So in this video, what I'm going to be doing is adding a timer circuit to this to flash the LEDs. And for that, we're going to be using one of the most popular chips on the planet, the NE555 timer. Now, one or two people asked questions from the previous video on why I didn't show how to create the cable going from the USB charger direct into the board here, rather than using this little power supply here. And the fundamental reason really is that unless you've got a soldering iron and a number of bits of equipment, then it's probably not that straightforward to create. What I have done, I've added to the description of the previous video, we've now got the Ben Eater on making a USB 5V power supply cable, and I've also added the links for the USB power supply cable, the breadboard power supply, and the mini digital voltmeter. So those have all been added on there, and there will be a link at the top of the video to take you to that previous video. This is the second video in the how to use breadboards and retro digital electronics, and in this video we're going to be looking at the 555 LED Flasher design. So this is how I've mapped out the tutorial series so far. So this is the LED Flasher design, then we'll look at resistors and capacitors, in particular how to understand the markings on the resistors and capacitors. Then there'll be wiring up the flasher circuit, then we'll do some tidying up and playing around with the flasher circuit, and then we'll get into the logic gates and chip families and going through all of the chips that we actually need to get an IBM PCXT working. As we covered last time, the NE555 timer was designed in 1971 by Hans Kamzin for Schematic, so he was working as a contractor for them at the time. Since then, up to about 1 billion of these have been made per year, so estimates vary between about 30 and 50 billion of these chips have been made. The 555 timer incorporates the equivalent of about 25 transistors, 2 diodes and 15 resistors, all in a small 8-pin dual inline package. Can drive up to 200 milliamp load, is more than enough to drive any LED. Now, the flashing LED circuit is going to require us to look at the integrated circuit, looking at resistors and capacitors. I should say I'm not going to go through in great detail explaining how the 555 timer works. Ben Eater has actually done about 3 videos explaining how he used the timer to create the clocks for his CPU project. And this is a video here, so I include a link for this video in the description. So this is the first video, and he goes through drawing out a hand sort of drawn diagram here. And you'll see when we look at the documentation that in fact the diagram now looks quite similar to this. The original diagrams in the datasheet weren't very clear. The only difference really is this discharge transistor on Ben's diagrams up here, and when we look at our diagrams it will be over here. But if you want to know how the 555 timer works in great detail, then follow this link for these videos, and there's about two or three videos you need to watch, and I'll tell you in great detail how it all works. What I'll try and do is to summarize those series and videos in a couple of minutes. So let's just take a look at the data sheets. So this is a Texas Instrument data sheet from about 10 years ago, and this is a schematic diagram of the transistors and things in the chip at that particular point in time. Unfortunately, the rest of the data sheet, some of the information in it isn't particularly great. 1 or 2 of the diagrams have even got some errors in them. So in fact, in this particular diagram where we have the voltage divider here, then the link going from here to this comparator appears to be missing. So Ben mentions that in his video with the reason for him drawing his own diagram. The latest diagrams, so this is the current data sheet from Texas Instruments, is much better. And there is this diagram here. And if we just zoom down to where that's defined, you see this diagram's closer to Ben's diagram, the only difference being this discharge transistor rather than being up here in Venn diagrams down here. So it makes some of the drawing of the external components we need to add this a little bit more complicated. We're not going to spend a lot of time looking at the data sheet, but just to say that in here it actually covers the number of modes of operation. So you'll hear these terms monostable, so that's like a one-off pulse. So if we were trying to clean up a push-button switch, for example, so quite often debouncing the contacts that sometimes bounce up and down very quickly when you depress and release a push-button switch. So that's what that can be used for. But we're going to be looking primarily at the astable operation, which is basically how we get an oscillator output. And we're going to be looking at trying to flash the LED up to about probably 3 times a second. And we should have the on time and the off time, or the mark and space time, at about 50-50. And in here there are various equations that have been included to tell you how to actually calculate the on and off time and the frequency. Now we'll be using some pre-calculated values rather than having to go through the details of that. And then just for interest, this is the original Signetics 1973 document. You can see here the diagram's not terribly clear, and this was actually a document that was put together around that sort of time to tell you how to use a chip. And there is some useful information towards the end. There's quite a number of example circuits, and also there's a couple of hints and tips and things on certain problems and things that you could avoid, particularly with diodes and a few other things there. So I'll include the links for these in the description below if you want to go off and have a look at that. So this is the diagram that I've just shown you, and what I've done is I've augmented it a little bit. As I said, the diagrams in Benita's video had this discharge transistor up on the right hand side here, and it made the diagram look a bit neater. But I'm going to try and go through and explain it with the additional components we need to add to turn this into an astable multivibrator, so something which is going to turn the LED on and off. So first of all, we just need to do a little bit of housekeeping. So we're not going to be using this control pin or the reset. So the reset will just be tied to 5 volts. And I think the control pin will probably just have a capacitor tying it to ground, which is covered in some of the documentation, but we won't bother with that at the moment. Now the key thing really that drives the whole of this timer circuit is in here there is a voltage divider using 3 resistors, which just so happen to have the value of 5K. Apparently the product name 555 did not come from the 3 5K resistors, and it was just chosen for marketing reasons, but some sources will say that it's because of these 3 resistors. But when this is connected to 5 volts in this particular case that we're going to be using, then what will happen is that we'll have the voltages here will be divided into 1/3 here, 2/3 here. You see the voltage here will be about 1.67 volts and about 3.3 volts here. Now these two things here are called comparators, and what they will do is subtract the minus input from the plus input, and when the result is positive, then there will be effectively a 1 or an output voltage on here, and when input voltage here is above 3.3 volts here, we'll get a 1 on here, and when the voltage is between these two values here, we will end up with a 0 on both of these things. Now this stage here is called a set reset latch, or a SR latch. Now this is sort of a fairly standard simple logic component. And the way how this works is if there's a 1 on the set, then the output here will be enabled. Now in the normal cases, the SR latch normally has a Q and a Q bar, an inverted Q output here. Because of the way how the circuit is designed here, we only have the inverted output here, and then the Q is the output that goes off to the LED. So when this is set, this will in fact be set to 0, and this output will then be 1. And then when the voltage goes above 3.3 volts, then this will then go high, the reset will be enabled. But what that will also do at that point in time is when this is Q bar is true, then this will also enable this transistor here. And what that will do is anything that this is connected to will then discharge down to ground. And we'll see when we add the other components here how that actually makes our 555 oscillate. So first of all, we're going to have a look at the truth table for the SR latch. So as I said, we've got the set and the reset. So if they're both 0, it just keeps what the previous value was. When reset is 1, then we get a 0 coming out of here, and in actual fact this one will be true and this one will be 0. When set is true here, then we'll get this set to true, so Q will be true 1 here and this will be 0, and the situation when we both have 1s here is invalid and you wouldn't get valid output from here. So we're going to be adding an LED and an appropriate resistor to the output here. Now we might change the LED resistor value now in light of what we've been looking at, but we'll stick with 330 ohms for the moment. And then we need to wire up the discharge to one particular resistor here, and these two resistors here are how we calculate the periods of the clock. Now the key thing really that does the timing is the capacitor here. So a capacitor operates a bit like a sort of a very small battery, and in fact what happens here is that under some certain stages of the cycle, then the power will come through here and charge the capacitor here. Once the capacitor gets above 1.67 volts, then this value will change. Once the capacitor gets to 3.3 volts, then this value will then be set and will then enable the reset here, which will then make this output true, which then enables this transistor. So what that will then do is actually discharge the capacitor here through this path here, through the 220k resistor, through this transistor and down to ground. Now in the documentation what it will show you is what you'll basically get is at the beginning of the first time this runs, then it will start from 0, which will be down here. But on a regular cycle, it will start from just below about 1.67 volts. And as it enables this, as it goes below 1.67 volts, then it will turn off and it will charge up, charge up, charge up until it gets to this voltage. And then this will be enable this transistor, and then it will discharge through here. And it'll then come back down and they'll just repeat that forever. And what then comes out here is we get the high and low values coming out here, which turns the LED on off. So that's hopefully trying to summarize the best part of half an hour to 50 minutes of Ben's videos. And what I'm going to look at now is the schematic diagrams for how we're actually going to build this. So I'm first going to look at a tool called Fritzing. So Fritzing is a nice visual tool and is used, I think, by Adafruit for a lot of the information they put on their website. And it allows you to deal with a sort of a diagram of a breadboard and to actually drag and drop components. And if you see here, if we look at the 555 timer, and if you actually hover over individual pins, you can, if you click on the pin, it will show you what it's connected to. And when you hover over the pin, it will actually show you that's ground, that's the supply voltage, and this is the trigger pin, the output, reset, control voltage, threshold, discharge. And so we can also then click on the individual components, and if we click on that capacitor, we can see what the value is. It's a 1 microfarad capacitor. Click on the resistor, we can see it's a 330 ohm resistor, and we can also see we've got a 220 kilo ohm resistor and a 1k resistor. And then this is just a small capacitor that we put in on the control pin to stop interference, and this is the capacitor that determines the timing, the period of our flashing. And this capacitor here is just to decouple the power so we don't get any interference on the power lines. Now it also allows you to maintain a schematic diagram, and this is schematic for it. This is using sort of more the American style for the resistors. And you can see here that the changes you make here can get also reflected in the breadboard layout. If we added a wire on here, then we'd get a very thin wire appear in this diagram. We'd have to hook it up and decide how we want it. So Fritzing's a nice tool. I have used it in earlier series where I've used this for designing the Veroboard stripboard layouts for some of the things like the KiCad. But I find that when doing complicated circuits, it gets a bit cumbersome. But it's nice for doing sort of 1 and 2 breadboard sort of circuits. So certainly it's worth looking at if you're just starting out. You do need to pay about 7 or 8 euros, I think, to download it for the first time. But after that, then all updates are free after that. But the tool I prefer to use is KiCad or KiCad. And the tutorial that I'm looking at here what I tend to do is I tend to lay things out in the way how they appear on the breadboard. So you'll see that I put the power rails in here. And when we zoom into this, you'll see that the 555 chip here, we've got the pins going 1, 2, 3, 4, 5, 6, 7, 8. Now that isn't a normal way how schematic diagrams in KiCad work. This is a default chip that you'll get out of the box for the 555, and you'll see that the way how these chip layouts seem to be designed is that you tend to have the power rails on the bottom and the top, the outputs on the right hand side and the inputs on the left hand side, and that's great for if you're trying to make logical diagrams and things. But what I do is I take the standard here and then I rework it into a breadboard component, and I keep that in my own library. And the reason for doing that is it just means that then our schematic diagram here will pretty much exactly match the physical layout on the breadboard, and we don't have to do an extra step in actually taking the logical design of our schematic here and then making it into a breadboard physical output like you would have to do perhaps with a printed circuit. So this is the diagram for what we're going to be doing. So the only thing about the 555 chip is that it's a little unusual in that the power pins are slightly different. So most chips, certainly most of the logic chips, the ground is at the bottom left and the voltage 5 volts is on the top right. Here the ground is at pin 1, but that's not going to be a big problem. And we can see here that in order to wire this up, we've got to have our 1 microfarad capacitor. We've got our LED with its current limiting resistor here, and the cathode of the LED is going to 0 volts. We need to wire in pin 2 round to pin 6, and then the pin 6 and pin 7 are connected via this 220k resistor, and then there's this smaller one tying this pin up to 5 volts. And then this additional small capacitor here is recommended in the datasheet that you can get interference on the output, and putting this capacitor in will actually stop that interference. Again, Ben in a second or third video, I think, actually shows this on the oscilloscope and shows how he tackled that with using this. Then here, basically, this is just showing where we've got the R1 and R2 values. In fact, it's the labeling here is actually doesn't match here, but the R1 and R2 here are the two timing sensitive resistors here, and R1 is stuck at 1k the whole time. And by changing this value here and changing the capacitor value, then we can change the period from sort of like 3 kilohertz, 1 millisecond, all the way up to about 10 seconds. So we're going to be going for the moment with this one, 1 microfarad, 220k and 1 kilo ohm. So that should give us flashing about 3 times a second. One other thing I also do is that in order to prevent problems laying out in projects, I tend to create chip labels for sticking on the chips, which will actually have the pin names actually on the chip itself when we're using it in the breadboard. I'll just show you what I've done with that. So as a video on doing chip labels in the breadboarding playlist, I'll include the links in the description below. Inkscape allows you to do vector sort of diagrams, and what I've done is created many chip layouts. So these are the ones for the 555. You'll see the chip name is in the middle there, and then these things are size, such as when we print them out as a PDF and we don't include any scaling, so we print out like real size, then we can then glue these using a Pritt stick or a glue stick onto the chip. It just means when we're wiring things up, then we don't make mistakes. And this is the output PDF, and if I show you one of the other PDFs that we've used in earlier series, you can see that we've got chips for the processors and a lot of the other chips that we've been using in the earlier Breadboard PC series. So having these chip labels is a really useful way of actually trying to reduce the mistakes when you're trying to plug in things across, particularly when you've got 40-pin chips. It's very easy to get the pin numbers confused. So I'm going to finish the video at this point. In the next video, what we're going to be doing is looking at the resistors and the capacitors and how to read the different values and the bands and how the various components are identified. So if you don't want to miss out on future videos, then please hit subscribe, and if you could hit like as well, it just helps to make the videos available to more people. Thanks for watching.